I don't know really if there's a Herald here in this room. If not, I think we will manage to introduce ourselves too. We are Matthias and Frank from the CCC in Dresden. And first of all, I want to say hello to everyone and thank you for paying that much interest to this topic of intrusion detection systems. So the next about 45 minutes, we are going to talk about what's known as intrusion detection systems. We're going to cover different IDS technologies. We will have a look what you actually can do with it and how you get valuable results out of it. Here the agenda, quite briefly. First of all, of course, we have to define what we are basically looking for with the IDS systems. Then we will talk a bit about why you should use intrusion detection systems, what they are good for, what not. We will give you an overview of IDS technologies. Some of them are not really made as IDS technologies, but you can use them as such. Quite good. We will talk about basic problems involved with those things, and we are trying to show you some solutions. One of it will be a hybrid IDS framework. We're going to show you there still will remain a few problems, and we also will show you some approaches how to deal with it in correlating events those IDS systems are reporting. So starting with attacks or intrusion methods, well, we have to categorize them a bit. So the first class, anyone using Internet Explorer or Outlook will be very familiar with. Those are worms, viruses you might read about from time to time, or Trojans. For EDS systems, they are quite easy detectable because they make a lot of noise. I mean, they don't really try to cover themselves while they are spreading. Much more difficult to find is manual attacks using the CCC approach, cover, concealment, and camouflage. Those do not produce very much noise or basically things you can look for on your system or on the network. A different way to classify attacks is you can distinguish between local and remote attacks. So local attacks will be more or less everything that gives you higher rights on the system than you should have. You know, things like buffer overflows, format swing attacks, race condition, which will give you privilege escalations. Or for remote attacks, well, you also can use buffer overflows to use those systems remotely, install Trojans, rootkits, or bots of all kinds, or simply deny services the system is offering. Another thing you have to keep in mind that real life is most of the time much different from what you have here. Most of the time you have to deal with crappy software, you have to deal with zero-day exploits, you have to deal with boxes in your network you don't really know what they're actually doing. You know, from some vendor sends it to you and your boss says you have to have it. You will find some admins that like to go home bang on time, so they're not really looking after patches. And you also will have systems that are not patchable at all because the software doesn't run with recent patches anymore. And I'm not talking about Unix-like systems, but you can imagine it's more related to Windows systems. And of course you have to live with all kinds of trade-offs in those systems and those environments, you know, you find in the student network, on the internet, or on company networks. Actually, a funny story, I by accident I was listening to two people in this house, but not visitors actually. They were talking about how to discover if you're really connected to the web page of your online bank or not. And one was giving the proposal that you can use a wrong password, and if the page says the password is wrong, it's the right page of your online bank. And it really happened. You know, those people who were walking around in this red cloth, it was them. Okay, so what are intrusion detection systems good for? Of course, they're not there to compensate for bad security. I mean, if you don't take care of the security of your systems, IDS systems will not help you too. So they're really more there to recognize damage that might have happened to systems. They will help you to evaluate incidents, trace back intrusions, or well, basic for forensic analysis. So they help you really to discover what's going on your network.
Okay. I will continue. After you heard about the purpose of IDS systems, I will give you a short introduction about the different technologies that you can utilize for IDS. Basically, they can be divided into two groups that are the network-based IDS and the host-based IDS systems. Network-based IDS means that you have something that listens on the network and analyzes the packets that cross the wire. And host-based systems mean that you have something on the system itself that checks the, for example, files or what is going on in the system. I will continue with the network-based IDS, and the first group is a traffic analyzer. Analyzing traffic means that you capture all the packets on a wire and inspect their content, for example. One of the most popular traffic analyzers is Snort. Snort uses two steps for the processing of the packets. In the first one, it passes them to a preprocessor, which can be used to detect port scans. It can reassemble TCP streams from the packets in the right order, which they were sent out. It can decode some higher level protocols, for example, RPC or HTTP, and it can also be used for virus scanning with the ClamEV plugin. In the second step, Snort uses a pattern matching engine where it can be configured to detect traffic patterns of, for example, exploits or every kind of traffic, and also for detecting protocol violations. On the next slide, you see two rules of the two signatures of Snort. The first one is quite easy. It only detects TCP packets from any interface from the external network to the home network. There's some kind of aliases that must be defined, but it's not relevant for this example. From any port to port 23, that means every packet on this, every TCP packet will raise an alert for this rule. The second rule is a bit more complicated. It is a real example from a real Snort rule that detects NetBus backdoor activities, and it contains additionally, for example, a flow direction where here from server could be also in the other direction, or content. You can match for different contents on this rule. Sometimes it's not efficient only to look at the content of the packet. Sometimes it is also interesting who is talking to whom. And a technique which makes this possible is traffic accounting. For traffic accounting, there is a standardized protocol. It's called NetFlow. NetFlow is invented by Cisco for traffic accounting and billing purposes. And the implementation of NetFlow, you can see on the picture, consists of two parts or two components. The first one is so-called flow probe, which is software that could be implemented in the firmware of a router or on a PC. That this software counts every packet that passes the router, in this example, and exports these informations to a so-called flow collector, which is the second part of the implementation. The flow collector receives the packets and stores them on a database or what else for further processing. So the value for IDS is that we can detect anomalies in network utilization. The last network-based technology that I want to introduce you are the virtual honeypots. As you might imagine, analyzing and accounting traffic is not the real thing because it raises many false positives. So you cannot say if the detected events are really an incident. So with honeypots, you get a facility to improve the value of these events. Honeypots are basically dedicated systems with traps. That means you can run on these honeypot services, for example, a web server or a file share that can be accessed from everyone on the web, not from the web, from everyone in this network. So, but with the exception that this system has no production purpose. So an access to the honeypot is always suspect. Honeypots have, as real honeypots, have one big disadvantage. So because they are costly to deploy, that means when you run Windows honeypots, because you want to catch Windows worms, you have to buy a Windows license for them. So a possible solution could be virtual honeypots, like the Honeybee. Honeybee is a virtual honeypot, and it's able to emulate whole networks with routers and switches. All network latency times can all be configured. It emulates hosts with fake identities. You can say Honeybee that it should be appear as a Windows NT system or Linux or a Cisco router based on the Nmap fingerprint database. It has a scripting interface for services, so you can run fake services, can emulate an open mail relay, for example. And it can also forward ports to real existing services somewhere in the network. So virtual honeypots are a supplement for qualifying IDS events. It gives them a higher value. Now we come to the next big group, that are the host-based systems. The first one is syslog. Syslog, maybe many of you know already. It is a centralized logging facility. Exists in almost every Unix system. There are implementations for Windows also. Syslog, analyzing the log files provided by syslog, tells you about failed or successful logins, access to services such as web servers or mail services, firewall, the packets that will be accepted or blocked, or creation of new users or hardware events. Syslog can also be utilized as a network service on an external system. That means if you log to this external system, it would be very hard to wipe out the logs because this is external, not on the attack host itself. There are also some tools which help you to deal with the information in syslog, because the files can grow very big. No one would get an overview on them. So, for example, with logcheck, you can get a summary of files and send the administrator an email with special configured patterns. The next one is file fingerprinting. The value of file fingerprinting becomes clear when you remember the Unix philosophy that everything is a file. So you have real files, links, symlinks, Unix sockets or pipes, named pipes, that could be files. And file fingerprinting means that you calculate a cryptographic hash of the files and stores them on a secure place, or yes, and with file fingerprinting you can detect changes in the files, in the content of the files. For file fingerprinting there are different implementations. One of them is Samhain as an example, which offers some additional features. It can detect changes in file access rights or access times, modification times, the creation of new files, changes in user and group configuration, user and group rights, deletion of files, and also detect kernel rootkits on Linux and FreeBSD. The value for IDS is also very clear. You can detect the manipulation of files with them. Beneath the former introduced host-based systems, there are also some system integrity checkers that I want to mention only for some examples. For example, with check rootkit, which looks for traces of known rootkits, Tiger, which looks for programs that open sockets for listening, or evaluates package databases for unknown files. That means when you have a directory, user sbin, and there's a file that is found in no package of the operating system, that maybe somebody put the file there for any attack reason. You can also some different tools to do with vulnerability checks on installed packages or installed software, and also use historical performance data for detecting anomalies. For example, when the system activity raises very suspect. The advantage of diversity of tools is if some of them, the log file of some of them gets deleted, maybe another one has catch the event also. The last IDS technology that I want to introduce to you is systrace. Systrace is the implementation of a security layer, which at the kernel level, it is implemented in the base systems of OpenBSD and NetBSD. There are also patches for Linux and FreeBSD. Systrace enforces a policy that allows a particular user to execute syscalls or not. It means there's a policy manager that will be asked every time a syscall should be raised. And yes. If a process violates its policy, the denied syscall will be also logged to the syslog. And there are also some similar technologies, the role-based access control, for example, grsec and rsbug on Linux systems.
So now we have seen many different technologies. Most of them were not developed as an intrusion detection system, but can be used as such. since most of them log failed attempts of what they are actually trying to protect. However, all those different implementations were really not designed to work together in any way. So each system was built on its own island, and it's quite difficult to combine them in some way. Well, to give you an idea, what I mean, Snort, for instance, it can log to its own MySQL database, it can log to flat files, to binary files, but all this is very special to Snort. NetFlow, we have seen it sending UDP packets to the collector, and there the information is on, but not on a central system. With syslog, we have those flat files. You can pass them, but it's not really that you have them in one central database or something like this, where you can do further evaluation. With Samhain, well, same thing. HoneyD, same thing. So you have a very distributed data storage. So each system, again, its own island. And even if for some of them do exist quite nice tools to do analysis, looking, filtering, and stuff like this, you won't find a single tool that can look at the data of all of those different tools. So what would you do if we were able to design such a system from scratch? First of all, we want to have a standardized storage format. So all those different IDS systems should use one data format to store the information. Next thing is we want to have all this information on one place, let's say one database. So we can dig out all this information from there. And further, we want to have a common analysis tool, so we can have one tool we use to look at this data.
One of the main problems was, as Frank already said, that the sensors provide different data formats. You have the NIDS systems that provide, for example, IP addresses, TCP flags, or packet payload, which are very different data from them that host-based IDS systems provide. That could be file names or access rights. So how to store this in a general format? The solution is the XML-based IDMEF. IDMEF stands for Intrusion Detection Message Exchange Format, and this is an object-oriented format. It provides classes of alert objects that can be easily extended to fit for every kind of sensors. You can insert objects for representation of files or IP address ports. It's very configurable. IDMEF is not just another file format. It is a draft from the Internet Engineering Task Force. So it is very probably that this format becomes the new standard for intrusion detection message exchange. It means an RFC. And as a conclusion, this is one format to store them all. In the next slide, I have a very minimalized example of an IDMEF message in XML notation. You see there is every message gets an alert ID. This is a unique ID. It gets a timestamp, but it's not the only timestamp. An IDMEF message contains 3 timestamps for creation time, detection time. This is very different. And here you see the representation, for example, of an IP address. You have the source. The source is the source host in this case, and the representation of address. The remaining problems was that we need centralized data storage and a centralized analysis tool. While evaluating different approaches, we found an interesting framework which is called Prelude IDS. The center of Prelude IDS. The center of Prelude IDS is a so-called Prelude Manager, which is a server which stores IDMAF information to a database. This database can be in MySQL database or PostgreSQL. So there is an abstraction layer that handles the access to the database. On the other side, you have your IDS sensors, and these sensors can be connected with a special library to the Prelude Manager. So there is the connection from the sensor to the manager is encrypted with TLS, Transport Layer Security. And on the other side, I forgot. libprelude has an additional features. It maintains a local cache for the sensors. That means if the Prelude Manager is not reachable over the network, for example, fail-safe reason, the local cache it acts as a kind of buffer for the data, and when the connection comes back, the buffer will be flushed to the manager. Prelude also consists of an IDS console. This is a web-based console. This is called Previca. Previca uses also the Prelude, as libprelude database library to connect to the database. And it looks like this. We have it here as a little demo. You can see there are the events. We have some generated beforehand. So here you can see an user authentication, an host-based event, and user authentication that has failed, was detected. We can click on them and get deeper and see there's actually 2 events, and can also get a detailed view on them. Here see the times that I mentioned before, and the creation time, detect analyzer time. And you get information about almost everything. You can also see these heartbeats here. These heartbeats are information that the sensor send periodically to the manager to send him a message that the sensor is still alive. This also can be seen on this view, where you can see the status of the sensors. So that's okay. You can use almost every sensor or IDS system for Prelude, but as you can see on the slide, for some projects, for example, Snort and Samhain, are already Prelude enabled. Other sensors that have still no support for Prelude can be utilized by the Prelude LML sensor, which is a very special sensor because it is able to parse log files, is configurable by Perl-compatible regular expressions, so you can grab the information you want out of the log files and put them to an IDMAF structure and pass this to the Prelude Manager. For very special cases where you cannot use Prelude LML, you can also use a client API, which is available for C, Python, and Perl, which is a very comfortable way to send IDMAF events.
Okay, so now we actually solved somehow the 3 design principles we were aiming for, and are we happy now? And set with what we aimed for. Actually, no, since, you will have multiple sensors employing very different sensor technologies, and those sensors will generate many, many events. And some of those events might be sensible. Many of them will be false positives. For an example, I mean, if a system is attacked with buffer overflow, it's not vulnerable. You're not really interested in this information. And to to tune all your different IDS sensors is quite time-consuming too, even if you have to do it, of course. So a human admin might be unable to investigate into any single event that's reported by the sensors. And further, a single event doesn't really give you a shape of an incident, where most of the time different IDS sensors will fire. So the remaining problem is that we have simply too many events. So why not using them, correlating them to find out what really happened? So here we have a very, very simple and basic example of a, let's assume, worm attack. So what the worm does is first it sends an ICMP ping to see if the system it wants to attack is alive. Then after a certain time, it will send a buffer overflow. And if this buffer overflow is successful, the worm distributed, it will change some file that actually shouldn't be changed on your attacked system. So what we can do with this basic correlation approach is we say, okay, if this happened and this happened and this happened, we will have an incident. The problem with those sharp rules is that they might be too exact for dynamic behavior of the attacks as you find them. In this example, we try to visualize that if the ICMP ping is a bit too early for some latency, you know, if a worm spreads, I mean, your network hardware gets a bit overloaded. So it might take some time till you get an answer. So in that case, you would come to a wrong conclusion. Actually, to introduce to you a more advanced approach to do this, first we have to tell you a bit about so-called fuzzy sets. I mean, who of you has ever heard the term fuzzy control or fuzzy logic? Wow, that's really a lot. Okay, for the other people, I try to explain it with a very simple example you find in most textbooks. Sets, you know, from school are a very sharp definition of what values belong to the set and what values don't belong to this certain set. So if we define a set called warm, we could say every temperature value that is above 23 degrees belongs to the set warm and others don't in that case. So what is about 22 degrees? I mean, it doesn't belong to the set warm, but for sure it might not belong to a set called cold or representing what's cold. So humans actually think a bit differently. They would say, I mean, yeah, maybe it's not so warm, but they still would use the term warm. And this actually is used in fuzzy sets. So you define a so-called membership function, and this membership function tells you how much your value belongs to your set. In this case here, we have a membership function, which is a ramp in the beginning, set from 5 degrees up to 23, and then the membership function gives you 1. And for the set cold, we have a similar thing. So this is warm till 5 degrees, and then you have this ramp. So a temperature of, let's say, 18 degrees but I only can guess it, will belong to the fuzzy set warm by 0.7 and to the set cold by something like whatever, 0.4. So fuzzy sets are more a mathematical representation of how humans use this term set. Of course, you can have many more membership functions. Here are a few of them. The first one is this sharp classical set. You also can have this trapezoid membership functions, triangular ones, and well, you can use Gauss functions or E functions, and there are many more.
So, you just heard about the idea behind fuzzy technologies, fuzzy sets, and so we can make use of them for IDS. The first one would be to formulate a so-called fuzzy rule. Each fuzzy rule must contain the events we're looking for. Each event gets a so-called membership function assigned with also the parameters which can modify the shape of the function, and also limits and so-called repetition function. The repetition function is responsible for catching multiple events when multiple events match the rule, and you are only interested in the first or in the last event or some kind of average value. The second step is to evaluate the fuzzy rule. So you have to search for the matching events at the beginning, and then you can calculate the grade of membership for each of them. And in conclusion, you can do the correlation step, and in this context you can interpret the membership grade as a kind of probability value and use the multiplication, like in the likelihood theory, to get a final result for the correlation. This is an example for the correlation. As you might remember, the example from Frank in the beginning was a similar attack or incident. For each event, we assign a membership function. For example, for this file changed event, the square function, for the buffer overflow, we know that it appears about 2 seconds before the file change event. This is only an example. And the ICMP ping, we expect to appear 1 second before the buffer overflow for demonstration now only. So for rating the value of the events at a particular time, we have to set a point of reference. Typically, we choose for this the most critical event, which is in this example that the file has changed. And related to this point, we calculate the values of the membership functions. So we got for the file change the 1.0, because it is the event itself that we set as the reference point. The buffer overflow will be rated with 0.9, and the ICMP ping with 0.8. And as you can see in this box, we can use the multiplication again and get for the final result 0.72. And this value can be used could be interpreted as a kind of risk level.
So using those fuzzy rules can help to improve the correlation results. If you do wider rule definitions, you will get a wider range of results, of course, and doing the opposite and using more precise or more sharper rule definitions, you will get a more precise result, but in a narrower band. You have adjustable parameters to stretch or compress the membership functions to catch more or less events. And if you have multiple events matched by those membership functions, you have to somehow rate the quantity of those events. As Matthias just said, is you can use the first event you found or the last one or some median of those events you found. And you also can take into account the number of events you found. So we implemented this fuzzy rules in Perl. So you basically have to write a config file where you define the membership functions and the events you're looking for. Then the so-called correlation module is using the Prelude database to look for those events and calculate this probability value. This value that gives you an idea if this incident has happened or not. Next steps is that we want to code some report generation so that you, for predefined rules, you can generate reports. And in a more real-time application, we want to use instant messaging with a level of escalation to inform the admin of events we found, or of incidents we found using those fuzzy rules. So the conclusion for this talk is use all the data sources you can get for intrusion detection. Use clever methods to summarize, correlate, and evaluate this data. I mean, you don't have to use those fuzzy rules or other things, but most of the time it helps you if you use an application that summarizes your log files and looks for things that shouldn't appear there. And of course, look at those reports. So now we have some time for questions, if you have some.
Okay, so at the beginning you said if you use different tools, so the tools, if somebody was tricked a tool, you have another tool who can probably find that there's something going on. But if you centralize everything on one database, on one manager, so if somebody don't find out a way to compromise the manager, the complete IDS is for error. So don't know. So you can compromise the complete database. So the complete protocolizing in the central manager is helpless.
Yeah, I mean, at the end of the day, you are absolutely right. If you can compromise the central database and you don't have a backup for this, you know, something like you log everything that goes into this database into another one, you're right. I mean, if you lose your data in the central database and you don't have...
Yeah, but for an IDS or for me, it is not... I think it's not the right way for security. There's no redundancy. You have a single point of failure, the database manager. if I have the IDS on different systems, so I have not the ability to make an instant analysis of all logs, but I can take it every hour or more or less delay, copy it on a central on another station, external from the system, and take all the fuzzy things on the logs and import them by scripting from. So it's very hard to break in a system who was overviewed by different tools with different databases. So you have to trick every tool and you have to change every database.
Yeah, but
that's the standard today. And I can find, if I have more tools to run, second, third, so I find every time one thing in one of the logs. If I have a central database, so I can hope nobody find a way to compromise it. Huh? So I think
what you really can do is that any entry that is sent to your database, you can copy immediately to another database. That's, for instance, on a different system. So you have this diversity too. The thing we try to resolve is that you actually get more benefit out of your system if you correlate several events. And if you keep all this data on all your different sensors, I mean, there's no way in doing that, from my understanding. But you're right, I mean, I see your point, sure. And all I can say is take care of your central database, sure.
Hey, I do expect that the major problem is going to be that you have a lot of false alerts. Do you have any idea how can you reduce them? Because like the more fuzzy logic that you actually put into that entire IDS system, or actually in evaluating all those results, all the events, the more false alerts you will get.
Sorry, please, can you repeat?
The other way around. Don't you think the more events that you correlate, the more false alerts you get?
Well, that's actually what we try to avoid, because you know, if your snort sensor tells you there was a buffer overflow, as I said previously, I mean, with the knowledge of the system that has been attacked, you might know there is no IIS running on the system. That's an Apache web server, so you don't have to care about this anymore. And this is where you're actually eliminating false positives, because your network intrusion detection system doesn't know what the buffer overflow is destined for.
But that actually means that you need to head into more the direction of an asset management system. So you don't correlate like different IDS sources, but more or less an asset management, and then whatever, maybe even vulnerability management that is attached to it, and then correlate those information with with the current network activity, or however you call it, based on nits or hits.
Yeah.
Okay.
Thanks. Thank
you. In correlating data, have you looked in how far have you looked at the source IP addresses for correlating data? Do you assume that attacks will come from the same IP address? You will have a ping and ICMP from an IP address and a buffer overflow from that IP address, and then a file change. Well, you won't have an IP address for that, but in how much is that important for you in your experience?
Well, if you're in the central database, if you have the possibility to correlate all the data from different network IDS systems, for instance, you will have a chance to find out things like idle scans you couldn't detect with a single system. And so the idea behind correlation is that you really can combine different events you get out of your intrusion detection systems into an actual incident. So you can find out if this attack happened from this system and another one from this system, that the attack itself maybe is correlated to each other, but the several IP addresses are not. And you can use this in your rule set for finding incidents.
I understand the theory. I'm just wondering, I mean, I will always have someone pinging my network. I will always have someone sending the latest PHPBB exploit buffer overflow. So I'm wondering whether you will always really have to correlate the source IP address, and whether this will mean that attackers, to bypass an IDS that correlates data, will have to use different IP addresses to get past this, or to make it harder to be detectable.
Well, what you say is applicable to systems on the internet, I think.
Yes.
Yes. Well, since you're free to define your own rules, I mean, you can leave this out.
Absolutely. I was just trying to mention.
Yeah, okay, thank you.
Thanks.
Thanks. Okay, so there are no further questions. Thanks again for your attention. Thank you.
Thank you.